So if we use this queue structure, the performance of the system overall will depend on whether or not the boss thread has to wait when inserting work requests, toy orders into this queue. If the queue is full, the boss will have to wait. The time that it spends per order will increase, and overall the throughput of the system will go down. Clearly, if we have more threads, it's less likely that the queue will be full, but arbitrarily increasing the number of threads will add some other overheads in the system. So the question is, how many workers is enough? Well, we can add more workers dynamically on demand. Whenever we have yet another order, we go and call yet another worker to join the crew. This clearly can be very inefficient if we have to wait a long time for a worker to arrive. A more common model, therefore, is to have a pool of workers that's created upfront. With such a pool of workers or pool of threads, since a worker is directly supported by a thread, we don't have to wait for a new thread to be created or a new worker to arrive every single time we start seeing that orders start piling up on the queue. The question is, though, how do we know how many workers, how many threads to pre-create in this pool? A common technique is to use this pool of workers or pool of threads model, but as opposed to statically deciding what the size of the pool should be, is to allow the pool to be dynamically increased in size. Unlike the purely on-demand approach, these increases won't happen one thread at a time, rather we'll create several threads whenever we determine that the pool size needs to be adjusted. So this tends to be the most effective approach of managing the number of threads in the boss worker pattern. So to summarize, so far we saw that the boss workers model has these features. A boss assigns work to the workers, every one of them performs the entire task. The boss and the workers communicate via shared producer-consumer queue, and we use a worker pool-based approach to manage the number of threads in the system where we potentially adjust the size of the pool dynamically. The benefit of this approach is in its overall simplicity. One thread assigns work to all other threads perform the exact same task. The negatives of this approach include the overheads related to the management of the thread pool, including synchronization for the shared buffer. Another negative of this approach is the fact that it ignores locality. The boss doesn't keep track of what any one of the workers was doing last. If we have a situation in which a worker just completed performing a similar type of task or identical type of task, it is more likely that that particular worker will be more efficient at performing that exact same task in the future. Or maybe it already has some of the tools that are required for building that particular type of toy nearby on its desk. But if the boss isn't paying attention to what the workers are doing, it has no way of making that kind of optimization.